Dear all, it is a honor for me to make this presentation today. Thank you for the opportunity to deliver it. My name is Tomiczek. I am a lecturer and researcher at the Faculty of Mining, Safety Engineering and Industrial Automation at Silesian University of Technology. The title of the presentation is A Study of Rock Response to Failure in the Context of the Bending Properties and Comparison with Uniaxial Tensile and Compression Behavior. Plan of presentation. The first topic, abstract. The second, introduction, justification of the subject. The third, laboratory tests, materials and methods. The fourth, methodology of calculation. The fifth, results of laboratory tests. Sixth, conclusions. Abstract. The phenomenon of rock bending occurs during all underground exploitation, construction of underground excavations and tunnels, and even raising heating shafts. It is also common in building engineering, e.g., in the case of floors, rocks and concretes, as granular materials on the aggregate scale are fractured as a result of exceeding shear and tensile strength. In a complex state of stress, bending, crack propagation occurs from tensioned to compressed fibers. Three-point bending tests of medium-grained quasi-homogeneous and isotropic sandstone were tested for strength and deformation properties of rocks. The E-deformability modulus for compressed and tensioned fibers, as well as strains at failure, were determined. The results of three-point bending were compared with the results of uniaxial compression and direct tension. Clear differences were found in the values of strength moduli of deformation and strains at failure. Introduction, justification of the subject. A commonly used material constant describing the strength properties of rocks, but also concretes, composite granular materials and cohesive soils in the 1 and 3 axial compression strength. The use of these constants as a strength parameter is usually sufficient to solve most problems in the field of geomechanics, geotechnics, and strength at the engineering level. However, materials such as rocks and concrete are in fact fractured by shearing and/or tensioning, which already occur at the level of grain aggregates. Compression and shear tests are in common use, while uniaxial tensile tests are much less common. Failure of rocks is often due to flexure. Bending of rock layers occurs in the case of underground chamber roofs, mining excavations, tunnels, and even raising headings at high horizontal stress values. Also, in building engineering, the problem of bending of floors is key when designing ground-based and underground structures. Bending tests of rock beams are rare. This is primarily due to the difficulty of obtaining and making rock samples with recommended accuracy, as well as the need to compare with the results of outer strength tests, e.g. uniaxial tensile tests. Although the phenomenon of rock damage and failure occurs in many cases as a result of their flexure, issues related to rock stability are solved primarily on the basis of compression and shear constants. Similarly, in the numerical modeling, the basic constants are already mentioned constants and constants related to shear strength such as cohesion C or angle of internal friction phi. Few tests of Rocks indicate, however, that bending strength sigma b should not be equated with tensile strength sigma t. It also turns out that the properties of rock material subjected to bending are definitely different from that characteristic of rocks under compression or tension. Samples of medium-grained homogeneous and isotropic Brenner sandstone were tested. The properties of the sandstone have been well known as a result of research conducted in previous years. Brenner sandstone is a medium compactness light gray sandstone with a green, fine-grained shade with a random texture. A standard testing machine was used for the tests. Cuboid samples were made in accordance with the recommendations of the International Society of Rock Mechanics. Strains were measured by lattice strain gauges and by the strain gauge bridge. A system of the 6 strain gauges glued in the middle of the sample height was used. Photos show samples before and after tests. Methodology of calculation. Some authors, e.g. Hobler, equate bending strength sigma b with tensile strength sigma t in bending tests and state that sigma b is calculated, where sigma t, tensile strength determined in the 3-point bending test, F point load, L distance between supports, H beam height, B beam base. The figure at the bottom shows the theoretical fiber distribution and cross-section. The top figure shows the strain gauge system G, the bending moment M, and the bending stress distribution sigma. Knowing the value of bending strength, one can determine the value of the elastic modulus of tensile beam fibers, where EB, modulus of elasticity of tension fibers, sigma x equal sigma b concurrently after Jastrzębski et al. Results of laboratory tests. The results of the Brenner sandstone bending tests were compared with the results of other tests carried out in previous years. Brenner sandstone has already been subjected to uniaxial compression, uniaxial tension, and tensile tests using the Brazilian method. The table shows Brenner sandstone constants calculated on the basis of uniaxial compression, uniaxial tension, and tensile Brazilian tests. Uniaxial compression test, uniaxial tension test, Brazilian test, 3-point bending test. Comparing the values of strains at the failure strength obtained on the basis of 3-point bending tests and uniaxial compression and tensile, several interesting conclusions can be drawn. The absolute value of compressive strain of compressed fibers at the failure strength in the upper part of the sample under bending is lower than the value of tensile strains, tensile fibers, in the bottom part of the beam. It means that in the case of rock, where is no symmetry of deformation, all strain characteristics of samples under bending for both compression and tension fibers are non-linear over the entire stress range. The figure on the right shows the tensile and compressive deformations in bending. All characteristics are non-linear. The figure on the right shows the characteristics for uniaxial tension. All curves are non-linear, and the curves for uniaxial compression. The curves are both linear and non-linear. Conclusions. Rocks are granular materials. Their behavior in the field of compressive stress is well known. However, rock damage and failure often occur when rock layers bend. Rock layers are always bent as a result of underground mining, underground excavations, chambers, and tunnels. Two series of tests were conducted on the deformation and strength properties of homogeneous and isotropic fine-grained Berlin sandstone under 3-point bending conditions. The presented results of laboratory tests clearly indicate the differences between the values of constant calculated on the basis of 3-point bending, direct tension, and uniaxial compression tests. Differences also occur in the case of deformability moduli E. The deformability of rocks under different conditions is very different. The stress-strain characteristics for both compressed and tensile fibers of sandstone samples under bending were non-linear over the entire stress range. These rock material properties are important, especially from the point of view of researching and forecasting the development of damage zones in the excavation, ceilings and underground structures, mining excavations and tunnels, and in the description of the rock material during numerical analysis and simulations. Thank you very much for your attention and for the possibility of presenting this paper. Thank you very much. All who are interested are welcome to contact.